Hi folks, welcome back. Um, Hoping everybody's doing okay. I know we've got 3 weeks till Christmas, and then hopefully I will be back with you. I may try to drop in and see how things are going soon, but I'll definitely be on CNI and Impact to help out when I can, and we'll set up some after school stuff too to help. So tonight we are going to work on mirrors, and we're going to do the two major types. We've already done plane mirrors, and I hope you've got a good idea on how those work. But we're going to do concave and convex mirrors on this lesson. And so concave mirrors and convex mirrors. We're only going to do one that has one type of curvature at a time. The funhouse mirrors and things like that are the ones that have multiple. But we're going to be looking at three things. We're going to be looking at the three principal rays that we draw. Because if you'll recall, when you're looking at any particular illuminated object or lighted object, or even reflected light, light goes off in all directions, in all different kinds of directions when it comes off a surface, because you have to obey the law of reflection. And so our three principal rays that we're going to look at, instead of trying to draw lots and lots and lots, we're just going to draw three at a time. And those three principal rays are the one that is parallel to the principal axis, the one that is through the focal point of the mirror, and then usually we do one that is through the center of the mirror. We don't use this one. This is the one we ignore for mirrors. We use it a lot more for lenses. But the third one is the one that goes through the center point of the lens. Now, like I said, this one we will not use today. We'll be using the other ones to find our images. So the deal here is there's a couple of pieces of information you know. Number one, the focal distance which is represented by F0 or D0, excuse me, not D0. It's represented by F. Sorry. We're going to get our object and image distances here. The focal distance is F. It's the symbol we'll use. And yes, I know that's the same symbol we use for frequency, so be careful of context. But the focal distance is equal to 1/2 the radius of curvature. So what we're imagining here, and you guys have probably all seen these at some points in your lives, when you do, for example, a sphere. Let's just get a nice little circle on here to illustrate. So let's imagine that this is our circle, and I'm going to take out we don't want it filled. We want the outline to be black and heavy. Give it some weight. So here's our sphere. And when we draw our sphere, what we do to make it have that three-dimensional look to it is we're drawing. We draw it sort of like this. So we're going to pretend that the mirrors that we take are from these spheres, like Christmas balls. You know, the silver ones or the gold ones or the colored Christmas balls that are made out of glass. And we're going to cut out a small circle from that. And now, yes, it looks like a Pokemon ball. Sorry about that. But that's what we've got going on. So we've pulled out this sliver. And this sliver, when you look at it, will have a tiny little thickness, the thickness of the glass, and it'll be curved, and there'll be one side of it will be, like, for example, if this is a red Christmas one, red Christmas color on the outside, and usually on the inside then you have a silver. So it depends on which side we're looking at as to whether we're concave or convex. But the idea of the focal point, or the focal distance, is if I take the radius of curvature here, if this is r, the focal distance, the distance from the focal point to the mirror, f, will equal 1/2 of r. So the focal distance will be 1/2 of the distance from the center of the circle to the edge of the circle. So that's our first terms. Then we have a couple others. We have image distance, which is indicated with DI for image distance, or SI. I think our book uses Q. And then we have object distance. And object distance is indicated by a DO, distance for the object, or SO, arc length for the object, or the letter P. Every textbook does this with one of those three sets of letters. So when we're measuring things, what we really care about is how close or how far are you to the mirror. So what type of mirror, which type of lens, we got to know whether we have a concave or a convex. So let's start with that. And this section is really picture heavy. So what we're going to do is we're going to put a line in here, and this is going to be our principal axis, just like we would with any drawing we do, and that's your midline or your center line. And we're going to put a mirror on here. If I make this the back, let's make this the back, then the focal point would be over here. Focal point is always inside the curve. Okay, your focal point is always inside the curvature. So this is my mirror side, so this side is the front. In this case, this side is the back. And remember that this is a mirror. So when light comes passing through, and we're going to work with simple objects, the objects we're going to work with are going to be arrows, so that we can just get the orientation. So let's say I've got an object there. Maybe it's a soda can, maybe it's a toilet paper, maybe it's the candies in a gas station where they've got a mirror on the corner. These objects, we're going to represent all of them as if they were arrows, just to keep the visual image simple. And here's what's going to happen. There's going to be, from this, there will be rays of light that go in all different directions, up and down and out. There's light going in all different kinds of directions. But we're going to focus on just the two main rays that we're going to work with. Ray number 1 is going to come in parallel to this principal axis. So this is my parallel ray. And when my parallel ray hits the mirror, it is going to reflect back through the focal point. Always. Okay, so the parallel ray reflects out through the focal point. Okay, that's our first major ray. Then we're going to draw the second ray, and where the two outgoing rays cross is where our image is going to form, because the light coming off the mirror is what we see. We don't see the light going into the mirror, we see the light bouncing off the mirror. So we have to see where the light goes to see the image. So let's change colors here. Let's make this one blue. Our second ray is going to go through the tip of the arrow. Remember, these are going to start at the same point, and it's going to go in through the focal point and hit the mirror. So this is my focal ray, because it touches that same point. We're only looking at the light that originates in the same point. We want to see where the tip of the arrow is going to end up in our image. So we take two rays that both start from the tip of the arrow, and where they intersect again is going to be where they hit, and that's where the tip of the arrow is going to appear to be to us from the reflection. Now this focal ray always reflects back parallel to the principal ray. So it goes out parallel to the principal axis. So now we have an orange ray that's outcoming and a blue ray that's outcoming, and those two rays intersect. Where do they intersect? Well, they intersect right here. So I now know this is the tip of the arrow. It's going to form where the outgoing rays intersect. So I'm going to pause right there because I know you're probably copying. You can stop and pause this video, of course. But I want to give you a few examples so that you can get a feel for this. So on this one, our object was outside the focal distance. And so when we do this, I'm going to erase these. I'm going to do it with a new set. So let's erase these pieces. And I'm going to do all of this again through a different point. I'm going to take some of this extra stuff off. Take all these little, ooh, don't take the mirror away. You guys know sometimes racing turns into a mess. Just take some of this excess off. I'm going to take this out. Now I'm going to pick another place on this arrow. I'm going to figure out where another place on this arrow is. So a tip of the arrow is at that point. Let's pick another spot. Let's pick the middle of the arrow. It really doesn't matter where you pick. So now we're going to do another set. Parallel ray comes in parallel to the central axis. When it exits, it's going to bounce off because of the law of reflection. When it bounces off, and you can imagine this, the rays all get deflected at different angles depending on where they come in. So in this case, this ray will always get deflected, bent back. So here's the outgoing piece. I'm going to erase it, but I'm going to make it dashed now so that you can see this is not the original ray. This is the one that's the reflected ray. And it's reflected rays we care about because where the light goes is where we're going to see. Okay, so we have to be careful about this. Now, when we do our other ray, the other ray is going to go from that point, same point, but it's going to go through the focal point. And as we said, when it bounces off, it's going to backtrace here. So once again, now we can locate midpoint, midpoint. So if this is the tip, our arrow is going to have to go like this. And so now that we've located a couple of points, we can draw the image and we know exactly where the image is going to fall. I'm going to do this again for another concave ray, or concave mirror. This is called concave because the focal point is inside. Now let's classify this image as to where it's located, how big it is, and if it's real or virtual. So in this case, the first question is, did light pass through image? In our case, the answer is yes, the reflected light actually goes back through those points we marked. So this is called a real image because light goes there. The light actually goes there. The second thing we want to know is it closer or further to the mirror? Or further than the object? Well, in this case, I can see from my picture that if I was to measure the distance from here to here, here's your object distance, my image distance would be smaller. So it is closer to the mirror. And last but not least, the last thing we have to do as far as classifying here is it same orientation or upside down? Actually, there's two more. Same orientation, well in this case, it is upside down compared to the image. Or you will also hear us just say it is inverted. So we'll say inverted instead of upside down. Last but not least, the last thing we're usually curious about is magnification. Because curved mirrors typically make your object look bigger or smaller. You've probably seen in your car rear view mirror that your car rear view mirror says objects in mirror are closer than they appear. We're going to talk about what kind of mirror that means, what kind of curvature your rear view mirror has, but for now we'll just leave that they tend to get magnified. In this case, I would have to do math to see, but to me it looks like it's probably about the same size. And so the magnification would be close to 1. In other words, when you look at the original and you look at the image, they would be a 1-to-1 ratio in terms of size. We'll do the math on that later. Okay, let's do another one of these and then we'll classify it. And then I'm going to stop there and we'll do the concave ones, or excuse me, the convex ones on the next video. Whoops. I think I can probably do a little better than that. Okay, so here's my line. Now with AP, they don't typically show the mirror as being curved. They usually just do something like this. And they'll say it's concave, which means what they want you to think, and I'm going to show it the way it is just to keep it straight for you. Remember that if the focal point, let's make the focal point on this side. If this is the focal point, you have to curve around your focal point. So there's your focal point, this would be the front. So here's the back. Now this time we're going to make our object be inside the focal distance. So I'm going to put it in here. Okay? It's going to be in here. So here we go. In parallel goes out through focal point, get this a little bit bigger up here, and then we've got in through the focal point. You'll notice I had to start at the focal point this time. This is going to go focal point through tip, and it's going to reflect out parallel. And so you may say, here's your outgoing ray and here's your outgoing ray. You say, Miss Wilson, those two rays aren't going to come together. And I would say, yes, Grasshopper, you were very observant, because they won't. So what the world happens now? Well, remember what we told you about light. we perceive light as going in a straight line. So our brain thinks the outgoing ray started back here. Our brain thinks the outgoing ray started back here, so it perceives the tip of the arrow to be right there. You say, what in the world? Well, imagine every day when you stand in front of the mirror, what do you see? You see an image of yourself. And where does yourself appear to be? Well, it appears to be inside the mirror. Now, you know there's not an alternate reality you living in the backside of your mirror. There's just not one. But our brain, because of the way it perceives things, thinks that light came out of the mirror into our eyes. And so that's what's going to cause this sort of optical illusion here, is that the image that we now have is actually going to appear behind the mirror. Let's do another pair just to make sure that you understand what's happening. So we'll leave those two up there. That's our tip. So that's where our tip's going to be. Now let's pick another point. Let's pick a point down here. So now I do in parallel, hits the mirror, comes out through the focal point. And yes, Miss Wilson realizes that is not a very straight line. We're doing the best we can right now, so we're going to live with that one. So that one's going to kind of go whoosh like that. And then we've got the one that comes in through the focal point. That one's a little easier to deal with, and it's going to hit here, and it's got to come out parallel. So it's going to be going like this. Let me get that first one a little straightened up for you. Let's see if I can do that first one a little better. The focal point one's easier for me because I can line those up a little bit easier. So there's our, this is outgoing, but this is where our brain thinks outgoing came from. So our brain doesn't see this one at all. That one's gone. It thinks the light actually came from back there. When we do the other ray, the one that goes in parallel to the principal axis, the angle here is awfully steep. Oh my heavens. Yeah, not good. Let's see if I can get that a little better. This is why I recommend you use rulers, and I've got some in the room, and you will have them for the AP test for this exact reason. Okay. It's got to go out through the focal point. Got to go out through there, and it's got to go in parallel. So we're going to get, take that piece off, so this one is going to, these should cross right about here. They're not going to. Got it too small on my scale. But what we see is that the second one appears to be down there. So now we have tip of our arrow maps to there, point down here maps to here, and so our arrow must be, whoops, our arrow must be here. In this case, we would say that our image is virtual. It's virtual because light does not enter the mirror, does not go, or does not exist behind the mirror. Okay, that's our first thing. Our second question is it closer to the mirror or further to the mirror than the object? Well, these two look about the same distance from the mirror. So in other words, we'd say that object distance is about the same as image distance. It's clearly larger, and it is upright, where it has the same orientation. In this case, it looks to me like it's about maybe 1 1/4 to 1 1/2 larger than the original object was. So this is, for those of you that wear makeup, this is the compact mirror. In your mirror that you have in a compact, it's curved inward, if you will, so that when you hold it up to your face, you can see yourself closer. You can get a zoomed in view. So the mirror in those compacts is actually not a flat mirror, it's actually curved, and it's curved in such a way that it magnifies your face when you get inside the focal distance. It's the exact same thing that happens if you look at yourself in the front of a spoon. If you look at yourself in the front of a spoon from a long way off, you look like yourself, but smaller. That's our first one. And if you look at yourself really close up, then you look way bigger and zoomed in. Okay, so we're going to stop there, and that's going to be our concave mirrors. And the math on this is really straightforward, okay? Actually, I got to stop right there. I got to finish this off. Let's give you the math. So what does the math say? We're going to be using these two equations for all the mirrors and all the lenses. It's the same equation. So we use 1 over f equals 1 over do plus 1 over di. And magnification can be found two different ways. You can do negative di over do, or you can do magnification is height of the image over height of the object. So let's talk about what the signs do. In the first example, the focal point and the object were in front of the mirror. So they both get positive signs. F and DO are in front of the mirror. So they are both positive. So the number you put in, so F will get a positive sign and DO will get a positive sign. Both of those are in front of the mirror. Where did our image form? Our image formed in front of the mirror as well. And since our image formed in front, we will have image is also positive. So di will come out to be a positive number because it is in front of the mirror. And I'm going to show you an example of this here in just a second. The magnification, though, will have a negative di over do. So the magnification will be a negative number. Okay? It's a negative number. What does the negative number tell you? Well, the negative tells you it's upside down. And the fraction tells you the bigger or smaller. Just like if you were to do height, compare height to height, you would get a positive or negative. So the positive and negatives on magnification tell you whether you're upright, you're facing the same way, or whether you're upside down, you're facing the opposite direction. The fraction itself, the ratio itself, tells you the size. So let's work a problem with this. And let's just make some numbers up for the second one, okay? So I'm going to come over here. And let's make the focal distance 10 centimeters. And let's make the object distance 5 centimeters. We're going to not know the image distance. And so we're going to want to find out where's the image and how big is it. Okay, so we go, 1 over 10, positive fraction, equals 1 over 5 plus 1 over di. Alright, so I'll do that. This is 0.10. This is 0.20. It's 1 over di. So we get negative 0.10 equals 1 over di. So I put this over 1, cross multiply and solve. You guys are all pretty good at that now. So we get negative 0.1 di equals 1. So di equals negative 10 centimeters. All you have to check for here is that all the distances are the same unit. Okay, they don't all have to be meters or all be centimeters or all be whatever, but just make sure they're all the same unit like we usually do. So this says it's negative 10 centimeters. So what in the world does that mean? Well, it means it's 10 centimeters away from the mirror, but it's away from where? In this case, the negative sign tells me that it is 10 centimeters behind the mirror. This tells me it's behind the mirror, which tells me in this case that that image is virtual, because you can't, light doesn't go behind the mirror. Light hits the mirror and bounces off. So the negative sign means behind the mirror. And you'll notice that when I put that in, if I want to know the magnification here, to do the magnification, I'll do one more little box. Magnification is negative di over do. So in this case it's negative 10 centimeters over 10 centimeters. So it is 1. Which means the magnification here, oh I'm sorry, the do was 5. Miscopied. Focal length was 10. So this object is actually 2 times as large. Magnification being positive means that it's upright. We can see that it's upright, but the magnification being positive means it's upright. So if the original image, the original object was 3 centimeters tall, the image of the object will be 6 centimeters tall. This is why you get objects in mirror closer than they appear, because when you're riding in a car, the images are distorted in such a way that the car appears to be smaller than it should for how close it is to you. And that comes about because the lens is actually a convex lens. It bows out away from the flat surface. And we'll talk some more on the next video about that. So have a great day, and I'll talk to you guys later.